Today we're going to talk about Euler's formula. And to do that, I want to build up the understanding of Euler's formula from limits, derivatives, Taylor series, the just general stuff about complex numbers. So it's going to be a lot of content in this one, and I'm going to kind of gloss over a lot of important things, specifically for limits and derivatives. And that's because I want to focus on how these things relate to Euler's formula and how we build up to Taylor series. So keep that in mind, and also keep in mind that we will revisit limits and derivatives many times as they are crucial for, that they are the foundation of calculus, limits are. So let's just get into it, starting with limits. So our discussion of limits is going to be pretty brief, but let's start with an example. Suppose that you're flipping a coin with your friend, a coin that has a 1/2 probability of heads and a 1/2 probability of tails, okay? If it's tails, you win. If it's heads, sorry, if it's tails, your friend wins. If it's heads, you win. So after one flip, there's a 50% chance that you win. After two flips, there's a 25% chance that you win. After three flips, there's a 0.125% chance that you've won. When I say win, I mean you've won every single time. And so let's model this with a function. F of x equals 1/2 to the power of x, where x is the number of times x equals number of flips. And f of x is probability of winning all of them, of winning all. Okay, so as a sanity check, f of 1 is 1/2 to the 1, that's 1/2, 0.5. 1/2 to the second power is 0.25, 1/2 to the third power is 0.125. This isn't any calculus, there's no special math involved here. It's just setting up a function that can model our situation. Now I want to know, what's the probability if I flip the coin infinitely many times? What's the probability I win every time? So just purely logically, that seems impossible, right? There should be basically zero probability that I get that I win, that the coin goes my way every single time, right? And if we can't really plug in f of infinity. We can kind of logic through what that would look like. F of infinity, I'm going to do like squiggly equals 1/2 to the infinity, which 1/2 times 1/2 times 1/2 infinitely many times is basically zero, right? But infinity isn't a number in the same way that 7, 9, 17, 1/2 are numbers. And so this is not really an acceptable way to write this in math land. Really what we're doing is we're taking the limit as we take x to infinity. So this is notated as limit. The actually capital L versus lowercase l I think does have some significance in complex analysis because like with the principle now, but that's not really relevant here. So I'm just gonna use capital L because that's what I'm used to. Limit as x approaches infinity of f of x equals 0. So what we're saying here is as we let x go closer to infinity, x is a million, a billion, a trillion, a gazillion, f of x gets closer, f of x approaches 0 or is equal to 0. This limit is equal to 0. And if I graph out f of x, put f of x here, it looks something like this, where this is x equals 0 and there it goes and it looks like that. That's your classic asymptotic growth. And so once again, let's just back up and realize there's no value of x that we plug in to give us infinity. No matter what value I choose for x, this f of x can't equal 0. That is impossible. But the limit, as I go to infinity, is equal to 0 because it gets so close to 0 that it's basically indistinguishable. The formal definition of this uses things called epsilons and deltas, which is just a fancy way of saying if I have a point and I make boxes around that point that are successively smaller, eventually only that point is contained within those boxes. formal math people are gonna not maybe appreciate that, but that's the logic I use to think about that epsilon delta definition of a limit. I'm not gonna give the full definition here because I honestly think it's just distracting from the actual idea that limits are trying to convey. So let's look at another example. Let's say I'll use a different color now just to use blue. So let's say g of x equals x squared. This is just our very familiar parabola, right? So g of x equals x squared. And I ask you for the limit, oh, sorry. I ask you for the limit as x approaches 3, as x approaches, sorry, this pen's acting up. I ask you for the limit as x approaches 3 of g of x. What does that equal to? So let's say 3 is like right here, and f g of 3 squared is 9, so we'll say that's like right here. That's not, so that point is right here. That's 9. So we know the point 3 comma 9 is on g of x, right? And so the limit as g of x approaches 3 is equal to 9. But here, g of 3 is also equal to 9. And that's because the function is continuous. That's once again not maybe the most important thing for our discussion here, but I want to clarify that a limit doesn't really only apply to situations like this, where you're looking at as you go to infinity or as you go to a value where the function doesn't actually like exist. It can also apply to just any situation. And if you think about it, that makes sense. If I'm curious as to what value will if I make $100 a day, what value will my money approach after 10 days? It'll approach $1,000 because I mean that's just what my money is becoming. However, in situations like this, I will admit that limits are not as useful. Like just asking what is the limit as a function approaches this value of a continuous function of a very basic thing, it doesn't tell us that much information. However, as we'll see in the derivative section, that doesn't mean we can't do things with the limits. There's an interesting application of limits to derivatives that is actually how we define derivatives. So I was stumbling over my words there, but the big idea is this. As we look at the behavior, as we get very close to a point of interest, we are evaluating the limit of that point of interest. To reiterate, the limit as x approaches 3 of x squared or of g of x, which put brackets here for clarity, is 9. And even if I make it so that this function doesn't exist there, like let's say h of x equals x squared times x minus 3 over x minus 3. So this function is in some ways equal to just x squared itself. However, you can't divide by 0. Even 0 divided by 0, that's not a number. It's like what we call an indeterminate form, but it's still not a number. So h of 0 does not exist. However, this function still does look like that. It's just now it's gonna look something more like, and it's gonna have a hole right here because that hole being at the singular point of 3 comma 9 because we've said this function can't exist at x equals 3. But I can still take this limit as x approaches 3 of this function and say, as I get really close to that point, as to the point that would correspond to f of x and x equals 3, what value do I approach? And the answer is still 9. So in this h of x, the limit as x approaches 3 of h of x does not equal h of 3, but it equals what h of x approaches as we get very close to h of 3. Okay? So that's an important idea. We're looking at the behavior locally, very, very close to just at that point. So that is the big idea behind limits. And there's a lot of online resources and videos that give really intuitive visual explanations for that. Evaluating limits in practice is also not too difficult many times. There's a couple of funky tricks you can use, but those aren't important here. The mathematical trickery is not relevant. If you haven't taken anything away from the last 10 minutes, however long I've been talking, the big idea is just we are looking at the behavior very close to a point of interest until we get so close that we are basically at the point itself. So that's that. Now let's talk about derivatives. To open this discussion, I want to first talk about our good friend slope-intercept form, y equals mx x plus b, okay? This gives us a line with some slope, okay? So that's a remember that lines are easy to work with. If I say you're right here, I want to know what value you have 10x digits in the future. You just multiply by the slope and add it onto your original guy. And that's the big idea, the big reason why we really want to use derivatives. Derivatives can help us get these lines, which we call tangent lines. So to see why, let's talk about what slope really is. Slope equals rise over run. We should be familiar with that. You may also know that as your y2 minus y1 over x2 minus x1, because you're taking this coordinate's y value, this point being x2 comma y2, this point being x1 comma y1. And so you're taking the rise from y1 to y2 divided by the run from x1 to x2. So let's look at our function f of x equals x squared again that we looked at in the last slide. We have a parabola, looks like this. That's a bad drawing, doesn't matter though. Let's say we're interested in the point x equals 2 and x equals 3. It's not a great drawing, but it's okay. So I can start by saying, okay, well, what's the slope of the line between those two? If I just draw a line connecting them, we intersect at the points 3, 9 and 2, 4. And so the slope of that line, m equals 5. But now let's look at a point closer. Oh, sorry. And that this is called the secant line. This is a secant line. Let's choose now the point x equals 2.1 and 1. So we're looking at like this point right here and this point right here. It's going to look more like that kind of where we're still intersecting 2 points on the function. My drawing is not great, but to be clear, we're still intersecting the function at 2, 4 and 2.1, 2.1 squared, whatever that is. But now we're getting closer to the function only touching the graph at 1 point. And as we take the limit, as we take this point right here and make it go closer and closer to 2, so like x equals 2 and x equals 2.000000001, we see that the 2 points are so close together that the line is basically only touching f of x at x equals 2. We've created the tangent line, whose slope is the instantaneous slope of f of x at x equals 2. And that is the basic motivation behind why we use a derivative. We want the instantaneous slope of a function. And we can actually figure out a way to calculate this with just basic algebra and the algebra of limits. So let's think about what we were really doing here. We took a point of interest at another point that we took very close to that point of interest. In other words, we took the limit as that second point approaches that first point. So let's say our point 1 is just x comma f of x, okay? And our point comma 2 is going to be x plus some small other number, h, and then f of x plus h, okay? We want the limit of the slope of these two as h becomes 0. In other words, as point 2 becomes identical to point 1. So limit as h approaches 0 of f of x plus h minus f of x. That's our rise. Oops, it's annoying. F of x plus h minus f of x over x plus h minus x. This is equal to f of x plus h, same numerator, minus f of x, because we have no idea really what the form of f of x is. We just know it's a function. And then over h, sorry, limit as h approaches 0 of this. And that is equal to f prime of x. And this is our definition of a derivative, okay? This is a very, very important, you can call it a formula, but I like to think of it more just as a statement of logic, right? We're taking the rise over run, and then we're taking the limit of rise over run to get the slope. And you'll note that since we're letting h approach 0, it's kind of weird that we're dividing by h, right? Like we can't divide by 0. But what you'll find is when we actually try to calculate this in practice, if this limit exists, then we can calculate a slope there. If you can't divide out that h, then either you'll have to use some funky tricks to figure out how to get the derivative, or you'll see that the function just straight up is not differentiable, which is the differentiation is the action of taking a derivative. It's not differentiable at that point that you're looking at. So that's that's that. And the big takeaway from this slide is that f prime of x, or a derivative, gives you the slope at a point. It gives you the line that locally approximates that point, that function. So just another example, I guess. Let's take some random looking function. Let's say it looks like that. It's like a cubic. And let's say we're interested in the slope at this point right here. What we do is you take this limit and you calculate the value of this limit as h approaches 0 and as x equals the x value right here. And you'll end up with some number for f prime of x. That number is the slope of your line. That's what f prime of x represents. It is exactly the same as m right here. And just a quick note on notation. You may see derivatives notated as d over dx of f of x. These d's are not cancelable. Those are differentials, which we're going to talk about later. And actually having a good intuition for what differentials are is really the crux of calculus. It's not so much about all these limit definitions and all that, although differentials in themselves are a limit, but like just to be clear, you can't cancel these d's. It's more of a symbol than an algebraic term. So d over dx of f of x, I'll just say that you can't do that, equals f prime of x. Those are synonymous. Okay, so that is derivatives. Once again, many good online resources that get more concrete with what derivatives are, but just remember the basic idea that with the derivative, we can create a line that approximates the function at that point. Now, for those of you who have taken a calculus course like Calc BC, you may be surprised that I'm covering Taylor series before talking about integration. And while it's true that some proofs of Taylor's theorem, which is like what we're going to discuss here, really, or not, I guess not Taylor's theorem, some proofs of the form of a Taylor series involve an integral, you don't really need to understand integration to understand what I'm going to talk about here. And integration really deserves a whole lecture in itself, even more so than derivatives. So before talking about Taylor series, let me just recap what we've built up so far. Okay. If we want to create a linear approximation for a function f of x at x equals a, as where a is a number, linear approximation, we evaluate f prime of a. We want the slope equals slope of tangent at x equals a. where f prime of x in general equals the first derivative. Because f prime of x is also a function where I can also have lines. It gives you the slope at any point, or the instantaneous slope at any point on f of x. And so the instantaneous slope at any point on f prime of x is f double prime of x, which is the second derivative. Okay, so I'm going to take a step back from derivatives, but I'll return to why this is important in a second. We need to talk about power series to understand Taylor's theorem. So a series is a mathematical term for a sum of things. Crucially, a series is a sum. Okay, so a sequence is a list. Okay, so as an example, say I give you the sequence 1, 2, 3, 4, 5. This, which we put curly brackets around, is a sequence. Okay. The corresponding series, I'll call it S, equals 1 plus 2 plus 3 plus 4 plus 5, which equals 15. That's a series. Okay. It's really important to not get these terms mixed up. So just take a good note of that. Sequences are these lists, series are these sums. Series are notated in what's called summation notation, which we use a capital Greek letter sigma to write out. And you say n equals the term you're starting at. So for here, n equals 1, 2, the term that you're stopping at, 5. You don't write n equals 5 because what you're increasing is indicated by what you write right there. Of whatever you're interested in, which we'd normally write as a sub n. And here, a sub n, the sequence is defined by a sub n equals n. So the nth term in the sequence, as in a sub the nth term, is equal to n. The first term in the sequence is 1. The fifth term in the sequence is 5. The third term in the sequence is 3. A sub n equals n is what we're saying. The series that corresponds to this sequence of the whole sequence is given by this right here. The sum from n equals 1 to n equals 5 of a sub n, where a sub n equals n, and that's equal to 15. These say the same thing, but this is a more compact way of writing it. Okay. And there's ideas of convergence that are really important for assessing series, but we're not really going to talk about that here. We're going to focus on how this relates to power series, okay? And oh, sorry, before I get to that, this writing a sub n equals n might look a lot like a function, like f of n when I plug in an n equals n. But the very crucial difference is that f of n is a continuous thing. I can plug in like n equals 1.5 pi 17.38, and there's still an output for the other n. Whereas a sub n is a discrete thing. I can only plug in 1, 2, 3, 4, 5, 6, and so on. But beyond that, I mean, in effect, for what we're looking at, not much of a big difference. There are many important mathematical differences, but just not so relevant to what we're going to say here. So now let's talk about what a power series is. A power series is a function of x. So power series are functions of x, okay? And we write that as f of x equals the summation from n equals 0 to infinity of a sub n x to the n. So if I were to write this out just with the additions, that's a sub 0 plus a sub 1x plus a sub 2x squared plus a sub 3x cubed plus a sub 4x to the fourth, and so on, okay? Is basically writing it as a infinite degree polynomial. But these a sub n terms can be 0. the power series for x squared is equal to, I mean, it's still equal to a power series like this, a sub n x to the n, where all a sub n for n is not equal to 2 are 0, okay? And a sub 2 is 1. So the big idea for a power series is that you define some expression for a sub n that gives you these coefficients. Let me do that in a different color. That gives you these coefficients in your power series function, okay? And if you think about like sine and cosine and other things that are kind of not evaluatable in your head, I can't tell you, okay, what's sine of 13? You're not really going to be able to tell me that directly, but if you can get a power series for sine of x, it might be a difficult calculation to do in your head, but at the very least, given a four function calculator, you can actually evaluate that. And that's super important because sine is a lot more abstract than we might think. And so having this way to look at it is quite important. And that leads me into what's called a Taylor series, okay? The Taylor series for a function f of x is a power series that's meant to approximate f of x around some point. So t of x, that's what I'm going to call the Taylor series, equals the sum from n equals 0 to infinity of the nth derivative. I put n in parentheses. That's not f to the power of n. That's just the nth derivative at a point of interest x equals a. So we write that x equals a. F at the nth derivative over n factorial times x minus a to the n. Remember that factorial is like 5 factorial is 5 times 4 times 3 times 2 times 1. Just multiplies all the way down to 1. So just to be clear, this looks like f of a, that's just a number, the value of the function at a, plus f prime of a times x minus a plus f double prime of a over 2 factorial times x minus a squared plus f triple prime of a over 3 factorial times x minus a cubed. So, and so on, right? Now, that might be a bit of a difficult definition to wrap your head around, but let me plot out what that looks like to make really clear what I'm saying here. Use red for this plot. Let's go back to our little parabola. So our parabola equals some line. I can draw our tangent line to this parabola like this. But in reality, the slope of that line is changing at a rate given by the second derivative. And so if I include the second derivative, I get some better approximation. If I include the third derivative, for x squared, actually that wouldn't matter. But in general, let me give a different fun. Where's my cursor? Uh, sorry. So for a general function that just looks like, we'll say it looks really, really weird. Let's say it looks like this and then that. Okay. If I want to approximate the function at a value of x given by x equals a, we'll say a is right here. My worst approximation, the worst I can do is just that line that we talked about by just taking the slope of the derivative and drawing a line. But I can make that approximation better by including these upper derivative terms. And so I can get something that looks maybe like that by including the second derivative. If I include the third derivative, I might get something that looks like this. And eventually, as I include more and more and more, I get closer and closer and closer to my original function. Until at infinity, the Taylor series infinitely converges to our original function. This may not happen over all values of x. It happens on what's called a radius of convergence, okay? The functions we are going to be focused on, though, sine, cosine, and e to the x, converge over all values of x, though. And that's crazy. We can express sine of x as a series of something, and that equals sine of x. Like it is literally just equal to sine of x. No ifs, ands, or buts. Same thing for cosine, same thing for e to the x. That should be a really, really shocking result. To me, it is at least. And if you know about the patterns between the derivatives of sines and cosines and patterns particularly for the derivatives of e to the x, it might not be as surprising, but it's still a pretty amazing result. And I would like to say if you want more on Taylor series, in particular explanation of Taylor series that doesn't assume much background in calculus, like what we have here, 3 Blue 1 Brown's video is brilliant for that. I'm gonna move on to Euler's formula though, or not yet, but I'm gonna move on to complex numbers. So let's take a break from the calculus. Let's talk about complex numbers. Complex numbers, which we write as z, have a real part x plus an imaginary part y. So the real part of the real part of z equals x. The imaginary part of z equals y. Okay. Crucially, I mean, the imaginary part is not part. It does not include the y. It's saying what's the coefficient on the imaginary part. Also, crucially, complex numbers are just that. They are numbers. They aren't two numbers. They are numbers. And we represent them with vectors. So I can actually plot out this complex number on what's called the complex plane. This point right here, that's x, and this is y. And we draw it out from 0, 0. Okay? So I actually have I don't know, maybe it's not a great discussion, but I wrote a little bit in the lecture notes about why complex numbers are physically significant or why it shouldn't be that weird that complex numbers are physically significant because I mean we have negative numbers and it's kind of hard to visualize a negative number to begin with in the same way that you can't visualize a complex number very easily. So, or I mean concretely visualize a complex number. So it's um but I'm not really gonna talk about that here. So returning to this, that is how we plot a complex number. Just the magnitude of the complex number is the same way that we would calculate the magnitude of the vector v given by x, y, where magnitude of v equals square root of x squared plus y squared. Magnitude of z also equals the square root of x squared plus y squared. Um, let's also note, I just want to mention that this should not be that surprising. You have a component x right here. Adding any real number to this number z, 5, 17, 28.3, can only change x. And adding any multiple of I to this number z, like 5i, 17i, 28.3i, can only change this part of y, which is the same idea that we had with the vector v here, where if you remember our I hat is equal to 1, 0, and our j hat was equal to 0, 1. Here, our I hat equals 1, and our j hat equals I. And if I didn't mention it already, you guys aren't familiar, I is the square root of negative 1. You can't take a square root of a negative number, but that might be mathematicians decided that might be a useful thing to do, and so we defined I as the imaginary unit to represent that. There's some properties of complex numbers and their conjugates that I give in the lecture notes as well. That's not going to be so important here, but I will discuss the polar properties of complex numbers because that's a little bit important. So let's return. I'm going to redraw what I drew over there to our point x comma y, which is given by z equals x plus iy. This number, it might be convenient to look at it on a circle. So let's put an angle theta right here, and let's say this circle has a radius of r. So the r is actually equal to the magnitude of z, right? That's just the length of our vector, quote unquote. And theta is going to be equal to the angle between this line and the real axis. The real axis is the imaginary axis. Theta is going to be equal to actually the arc tangent of y over x, because if you draw a triangle, this is going to be, sorry, if you draw a triangle, this is going to be x right here, y right here. So tan theta equals y over x, so then you get to this. That's not really so important. In fact, this formula right here, arctan y over x, we're not really going to use, but that's very useful to be clear. What's important about this is we've now created a way to express our complex number in what's called polar form. And we can actually get a formula for x and y from r and theta. Let's draw this triangle out again to see how. It's a terrible drawing, but it's okay. This is theta, and x is this length of leg of the triangle, y is that leg of the triangle, and this length right here is r. So sine theta equals opposite over hypotenuse, y over r. So y equals r sine theta, and by the same logic with cosine, x equals r cosine theta. If you've taken calc, you'll recognize these as the formulas from polar. These also apply if we wanted to represent our complex number in polar coordinates. And getting a value for r and theta is really important here because of what we're about to talk about. So x plus iy, here's the big idea from this slide, equals r cosine theta plus r sine theta times I. This is x, this is y. Okay. Now here's the grand reveal. R times cosine theta plus I sine theta equals R times E to the I theta. This is Euler's formula. It is an incredible, astounding mathematical result that, I mean, every time I see it, it's just like, wow, this is pretty cool, right? And it's so essential in physics. I mean, we use this so much because it gives us a link between exponentials, which have very nice mathematical properties like e to the a, e to the b times e to the a plus b equals e to the a, e to the b. They're very easily separable. And cosines and sines, which occur everywhere in the real world. Cosines and sines are just things that go back and forth, which, I mean, a pendulum, a spring, me waving my hand, everything is waves. Light is a wave in a particle, or light we can model as a wave. So to understand why this formula is true, that's actually going to be one of your lecture problems. But briefly, I will mention it here. The Taylor series, and this is why I needed to build up the Taylor series to understand this formula. The Taylor series for e to the x is equal to the sum from n equals 0 to infinity of x to the n over n factorial, okay? And that's equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus and so on. This is actually how e to the x is defined for things like I. Because, I mean, maybe you were confused at first, or at the very least you should be confused now. How do we take e to the power of I? That's an imaginary number. Because we know exponentials to be like x cubed equals x times x times x. X to the seventh equals x times x times x 7 times. But x to the power of I is not x times, I mean, how many times? What does that mean? It actually just means we're plugging in x into here. So e to the I theta equals the summation from n equals 0 to infinity of I theta to the n power over n factorial, which you then plug x into there and you can see where it becomes. The Taylor series for sine and cosine equal, I'll give you cosine first, summation from n equals 0 to infinity of negative 1 to the n x to the 2n over 2n factorial, which equals 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. I'm just writing out a bunch of terms so it's obvious to see the pattern. Sine of x equals the summation from n equals 0 to infinity of negative 1 to the n x to the 2n minus 1 all over 2n minus 1 factorial, which equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus so on. So I'm not going to do it here, but it should be pretty clear that there's a relation between if we take some combination of cosine and sine, hint, hint, to get e to the x, hint, hint. So that is I guess, I'm actually not entirely sure if that's the rigorous math way to prove Taylor's form, the Taylor's series, or sorry, not Taylor. If that's the rigorous way to prove Euler's formula, as in like how he originally did it, but that's how you most commonly see it done. You might also see it done by just taking derivatives of e to the I theta, but that's not what we're going to do here. So, and I mean, this is once again just very, very, very important mathematical result. And honestly, if you just look at e to the I pi, sorry, you just look at e to the I pi equals cosine of pi is negative 1, sine of pi is 0, e to the I pi equals negative 1. It should be obvious why this formula is just so, like, incredible. You have e, the number that it's using the natural logarithm because you see e everywhere in nature. You have I, which is like a weird, hard to visualize, but apparently very useful square root of negative 1. You have pi, circles. You have 1, unity, and you have 0, which is, I mean, 0. You have these so many significant constants that are all linked by this formula. I don't know of any other formula in math that can say it can do all of that. This is just, I mean, it's such an incredible mathematical result. And hopefully this lecture did a decent job of like building up the intuition for that from limits, derivatives, Taylor series, complex numbers, and finally Euler's formula. And there will be some good practice with this on the lecture problems. So thank you.